So we're in Statistical Rethinking, second edition, chapter 11. We're in the medium difficult questions, and we're on 11 M7. We've recently been introduced to another function for fitting our models, the MCMC, the Markov chain Monte Carlo, whereas before we were using quadratic approximation with the quap function. The MCMC function in the Rethinking package anyway is called ulam. Okay, here we're going to compare a model that we saw earlier in the chapter using both quap, quadratic approximation, as well as Markov chain Monte Carlo with the ulam function. Okay, so we're going to look at the chimpanzee's data. So I've just copied and pasted this from the chapter, right? So we're getting our data ready, okay? So if you're unfamiliar with this example, you should probably read the chapter. It's the details of the experiment are a little bit more than I want to go into here, but if you've read the chapter, you'll be completely familiar with it. But we're going to model this like we did in the chapter. Well, this is what we used in the chapter. And so we are modeling how many times these chimpanzees pulled left. They had two levers, and they either pulled left or not, depending on certain conditions that they were under. And this was modeled as a random effect with actor, as well as treatment, where treatment was the condition in which they had to pull. Okay. So we fit this with ulam. We fit this with quap. I've already ran this, so we don't have to sit here and watch it churn. And so the question is, what happens in the posterior distribution? Okay, so these two columns are the posterior, the left two columns. There's somebody outside with a leaf blower, so I hope that's not too loud over the microphone here. But the left two columns are the ulam approximation for Pressey. Okay, so we have the mean and standard deviation, and then the quap. Okay, so if I'm looking through here, they don't look that different, although this one, I guess the biggest difference here is A2. Okay, so but there is differences here, and part of that difference is going to be just because of the randomness that is inherent to the runs of the models. But there's also going to be differences that are being caused by the fact that the quap has to use Gaussian distributions to approximate everything here, right? Whereas ulam, the MCMC, does not. Okay, it's actually sampling from the posterior and not making an approximation based on normal distributions. So, so we can actually magnify any differences here by allowing broader priors, which is what the question suggests we do. So we set the intercept, the random intercept, to have a wider prior, whereas it was 1.5, now it's at 10. Okay, so we're going to run this again, and again we're looking at the Pressey output, and now you really see at least this difference really jump out between the two models here. Okay, you see that the ulam model has a much higher mean value. Okay, so so why does that happen? Okay, well, the reason that that's happening is because the more permissive prior is able to entertain extreme values. Now, in the case of on the logit scale, those extreme values can skew to one side or the other. I'll show you what this looks like here in a second. But in normal distribution, those extreme values are going to stack up on either side of the mean, right? So if I run, so I'm going to extract samples from the two models, from the posteriors of both models, okay? And then I'm going to plot the A2 intercept, right? The one that is kind of the biggest difference between the two models here, okay? So so in black, we have the quap function, and you notice that it's very symmetrical, right? So even though we've allowed a looser prior, notice that additional variance is just stacking up on either side of the mean, right? But in the ulam model, where we are no longer confined to approximating everything with a Gaussian distribution, those extreme values can stack up on one side, right? Which is exactly what's happening here. Okay, so you see how the red curve, the ulam curve, is skewed in reference to the in reference to the normal distribution approximation. Okay, and that accounts for its much higher mean here. Okay, we'll call that good.